So, hi everyone again. Welcome to this second online workshop on key reactions in nuclear astrophysics. I would like to thank the speakers and the chairmen to accept our invitation, and I'm pretty sure we are going to have a very exciting day also today. And I think, I mean, it is fine. I ask the moderator of the first session to take the floor, and we can start.
Hey, can everybody hear me?
Yes.
Okay, good. Okay, so hi. I want to take a moment just to thank the organizers of this event for putting everything together, and also for providing me with the opportunity to be the moderator for this next session. My name is Kelsey Lund. I'm a graduate student at North Carolina State University. I'm also working with Los Alamos National Lab, and my focus is on our process, nucleosynthesis, and kilonova modeling. So I'm very happy to welcome you all to this first session of today, where we have two speakers who are going to tell us about what's going on in the study of the rapid neutron capture process. So with that, I'll just get straight to it, I guess. I'm happy to introduce our first speaker, Taka Kajino, with the National Astronomical Observatory of Japan and professor at the University of Tokyo and Beihang University in Beijing, where he also serves as the director of the International Research Center excuse me, for Big Bang Cosmology and Element Genesis. His research interests include astrophysical nuclear reactions, nucleosynthesis everywhere from the Big Bang, stars, supernovae, and neutron star mergers, as well as galactic chemical evolution, neutrino oscillations, and particle cosmology. So today he's going to talk to us about the origins of our process elements in the universe. And as a reminder to everybody, you can write your questions in the chat at any time, and we'll have questions at the end. And I will give you a warning when you have 2 minutes left. So whenever you're ready, the floor is yours.
Okay, I shared. Could you see?
Yes.
Okay, so we will. All right. Everyone, I'm very happy to see all your faces. And also, I'm very happy, pleased, and it is my honor to discuss with you on the origin of our process element in the universe. First of all, thank you very much, Aurora, and all the organizers for making these opportunities. Let's see, I will use my laser pointer. Okay, now, let us start our discussions. First of all, needless to say, we are very happy to live in the dawn of multi-messenger astronomy and astronuclear physics. It is because nuclei are the messengers of strong nuclear force in the universe, as well as gravitational wave, neutrinos, and photons. So we will discuss today the origin of our process elements, integrating all over these messengers informations. So this is my content to discuss today. The first, I will introduce the possible astrophysical sites for our process: supernovae, neutron star mergers, and collapsars. And having these possible sites, we will first discuss the galactic chemical evolution. And secondly, we will discuss the main subject of this workshop, KRENA, key reactions for our process. And finally, I summarize my talk. Okay, let us start our discussions from our excitement 4 years ago. Gravitational wave was detected from GW170817 4 years ago. And very excitingly, there are many possible indirect informations about the detection of heavy nuclei were reported. Unfortunately, the careful analysis of astronomers of all the measured recorded spectrum, that now all cesium, tellurium information have gone because the object is very excited at high temperatures, and the ejector has a very high velocity. So it is very difficult to identify the absorption lines as shown here as first reported. But instead, 2 years ago, they proposed that the strontium first ionized strontium may have been detected. This is indirect information, but it is enough for us to assume that some heavy nuclei, like hopefully the lanthanoid, were created in the neutron star mergers. Having this, now we will discuss a possible process in the binary neutron stars. But of course, the neutron supernovae are our main targets to study in the last 10 or last quarter centuries. Now we have two lineup of possible sites, but quite recently, there is another possible site that is a collapsar. The supernova is neutrons forming massive star evolution and explosion, but collapsar is a kind of supernova which leaves black hole as a remnant. So it is a very, very massive star evolution and our process, if possible, it were there. So we will today discuss binary neutron stars, supernovae, and collapsars as the possible sites for our process. So let us start our first discussion of galactic chemical evolution. This is a sketch of the origin of elements and until today, the origin of life. And the first star was probably exploded very short duration of time of 100 million years after the first stars were formed. And then they leave neutron stars to find the partners, and then they merge and explode. This is a second explosion. But the problem is the binary neutron stars should have a time delay because of a very slow gravitational wave radiations. So in order to discuss galactic chemical evolution, we should think of the cycle of star burst, evolution, explosion of stellar wind, and therefore the ejection back into the stellar, interstellar gas for the second generations of star formations and evolution. If this is a single star, like a supernova or collapsar, everybody knows how to parameterize the evolutionary history of these stars and the production of our process and the ejection. The stars, massive stars, which have a mass of M1 or M2, have a different time delay. This is a lifetime of main sequence. And after these times, they could explode and eject our process elements back into the space. So in the galactic chemical evolution, we take account of this time delay of a star lifetime. But the situation is a little bit different for the mergers, because first, the process starts from the binary stars born independently. But as a single star goes their lives, after some time of main sequence life, it delayed and explode. And then they should finally found the partners of neutron stars. But the problem is, from forming the binary formation, there is plenty of long time. This is the so-called quiescence time delay. How to estimate this time delay? It is very, very important because we know today our process elements. But if binary neutron star mergers as a site, there is a time delay. How to estimate that time delay? There is an observational fact of binary pulsars. Because of the binary pulsars, undoubtedly these objects are binary neutron stars. And having the observation of orbital eccentricity and orbital period, we could estimate by using the general relativity, the duration of time until the merging. And here we show the longest merging time expected from the observation is million times of giga years. And most important thing is lowest time is 100 mega years. So time delay is cosmological time scale. And here we show the first example of our calculated result of galactic chemical evolution as a function of metallicity. Here we show the faint and massive dwarf spheroidal galaxies and the europium to hydrogen ratio as a function of metallicity. And if you assume very naturally constraint from observation, 100 mega-year as a coalescence time delay, contribution of binary neutron star lands like this. Only quite recently in the cosmic history, they could contribute. But if artificially we put the coalescence time scale as short as 0.37 mega-years, it is very short, artificial. Some of a small faint mass, those little European abundance could be explained. But as pointed out by Benoit Coty, the recent history of European abundance and other R process elements needs at least 10 times bigger event rate of neutron star mergers. So only neutron star merger cannot create the solar system European abundance nearby our solar systems in the history. The last piece of a galactic chemical evolution is how to know the event rate. And very fortunately, for Neutrino-Driven supernova, which is the main supernova, event rate is known from the observation of aluminum-23 and in our Milky Way. Once or twice, supernova exploded. So we can use this event rate. And event rate times ejection of the total R process mass is a contribution of R process from Neutron-Driven wind supernova. Likewise, MHD jet supernova, it is very rare, almost 1% of ordinary supernova explosion event rate. And the binary neutron star mergers and the collapses, these are probably associated with gamma ray burst. So we can use the event rate of short duration gamma ray burst for the binary neutron star merger event rate. But the long duration gamma ray burst, nobody knows the correct event rate, even from observations, because even in a GW170817, there are many unsolved questions. Why they are faint? Why they are so collimated? Therefore, we here assume that the long duration gamma ray burst, namely the central engine is collapsars, is assumed to be having the same event rate as a short duration gamma ray burst, namely the binary neutron star mergers. Okay, having all this, we have calculated chemical evolution in a galaxy. Here we show the elemental abundance, isotopic abundance mass distribution as a function of metallicity or time. I will show you the movie here. From the very early history of early galaxy and very metal poor regions, the simulation starts. The early galaxy was dominated undoubtedly by the supernova and collapses. But the neutron star merger have arrived at a later time in our cosmic history. But the important point is, all these three, neutron star mergers, supernovae, including neutron-driven wind and MHD jet supernovae, and also collapsar, black hole forming supernova, can equally contribute to the formation of our process in the solar system abundance. So this hint us, we should study the nuclear physics of our process elements in all these possible astrophysical sites. So summarizing our result of galactic chemical evolution study, in the very early galaxy, supernovae and collapsar dominated. But as the time passes by, the neutron star merger start contribution, and these years, the three are equally contribute. Very interestingly, or unfortunately, even today, by using a big telescope, astronomers could not separate the isotopic mass abundances, but only elemental abundances. Although these different astrophysical sites of our process can make a different contribution and abundance pattern as a function of A, but the atomic number dependence is more or less similar. So our quest for astronomers is that please observe the event rate accurately and also separate the isotopes, not only the elemental abundances. in that sense, quite recently, it was interesting fact that under the deep sea sediment, Anton Werner and his collaborators have discovered the plutonium, which are coming from neutron star mergers or supernovae or collapsers, but as well as plutonium, the iron-60 were also discovered. So iron-60, these are coming from massive stars or supernovae. So in the near future, if these elemental or isotopic abundances are observed in deep sea sediments, we would be able to discriminate these two events, and also we could be able to constrain the event rate of neutron star mergers from the other supernovae. Okay, now having this result, it is time for us to discuss a quest for nuclear physics. We know in the neutron-driven wind supernovae and a MHD jet supernovae, not only heavy neutron capture elements and neutron capture and beta decay, but also light nuclear reactions are important. Is it so as well for collapsers or neutron star mergers? And second is the role of fission. Third is weak rates. And fourth is effect of magnetic field, because neutron star mergers or collapsers are probably strongly magnetized. So all these questions are in nuclear physics. So how to access to these questions? Let us try to understand each astrophysical site. First is the supernovae, leaving neutron star as a remnant. Here we show one example of our process nucleosynthesis in a couple of seconds after the collapse and explosions. Heavy elements are created. And this is the result. The neutron-driven wind supernovae is known not to be contributing to the second or third R process element here. Only the first peak or some light nuclear site of our process are probably created by neutron-driven wind supernovae. But the MHD jet supernovae, although its event rate is rare, can contribute, and especially the peak elements are created very well, but not enough for the whole range of nuclear masses. And in these nuclear processes in supernovae, we know that the start point is a equilibrium of neutron, proton, and alpha particles. And then these nuclei like Nucleus-78 are created, and then the rest of the neutrons are captured by Nucleus-78, and then our process goes on. Therefore, the light elements in the process from the first and second are important. So these are identified ever by theoretical calculation of supernova neutrino process, and also the MHD jet process nucleosynthesis. So let us briefly check one by one how accurately we know these reaction cross-sections. This is barium 7 gamma and alpha alpha. What we want to know is a reverse process. 2 alpha capture neutrons to form barium 9, but this is a triple reactions, so it is impossible to measure experimentally. However, by using a principle of the detailed balance, we can use the gamma photo disintegration cross-section to measure the forward reaction cross-sections. The gamma window energies for our process is here, very low energies. And here, unfortunately or fortunately, there are still 30 to 100% uncertainty. And this uncertainty is very, very important for collapsar or supernova R process, because this is a photo disintegration cross-sections. But as you see from this relation between the reverse rate, the 1 over E still is multiplied to the photo disintegration cross-sections. Therefore, low energy is enhanced more as a contribution to the forward reaction cross-section. In this sense, if we have 100% uncertainty here, this would be more drastically affecting the final result of our process. This should be measured independently or theoretically calculated. And theoretically, this looks like a resonance, low energy, 1/2 plus resonance, but there is no resonance expected for nuclear structure. This is a so-called ghost resonance. So we should consider the 3 cluster reactions, and its estimate is to be importantly done. Okay, next reaction is lithium-7 gamma and lithium-8 alpha N. And as everybody knows, there are 2 different methods in experimental measurement, inclusive and exclusive. And boron 11 has many bound states, which finally decay back to the ground state. Therefore, inclusive should include everything, and exclusive should separate all these. But the total sum of exclusive cross-section are, as you see, very interestingly or surprisingly smaller than the inclusive. Of course, error bar is very large, but this could be also measured again independently to settle the uncertainty. At the moment, uncertainty is at most 300%. And this helium-4 plus tritium and helium-3 plus helium-4 reactions, which are important for solar neutrino problem and also Big Bang nucleosynthesis, but these are important in our process as well. And for lithium-7 side, because lithium-7 is stable, electromagnetic structure is very well measured by high-energy electron-lepton scattering. Therefore, if we theoretically calculate the relative capture cross-sections, we can predict in this blue band. And then, with a conjugate reaction is estimated in the same scheme of clustering wave function to predict in this way. Although Adelberger and the world nuclear physicist and the theoretical physicist almost agrees, uncertainty is only 5% if you believe on these measured cross-section. But the mirror symmetry, as you see here, still cast a doubt of 5%. So we rate this abundance, this uncertainty is at least 25%. This also is one problem to be solved in nuclear physics. Okay, also oxygen 17 and gamma has newly estimated. Oxygen 17 and 16 or 18 are very difficult as a target because it is well, anyhow, because it is oxide. And new subthreshold state are contributing to enhance the reaction cross-section that neutron captures at most 80 times. Okay, all these uncertainty may be very, very important in the estimate of our process in nucleosynthesis. Okay, we will see later how effective all these nuclear reaction uncertainty. Before going that, let us sketch the second object of neutron star mergers. Neutron star mergers start from, of course, the merging neutron stars. Initial abundance is very different from supernova. Light elements are not created very much, but heavy nuclei are created because of initial conditions, at least in the dynamical ejector process. The wind contribution is probably small. And in these neutron star mergers, the fission plays a very important role. And as you see here, once the nuclear reaction flow reaches the fissile regions, they could not only split into symmetric fragment, but also the double-peaked asymmetric fragments. So we should estimate how their fission fragment distributions are from very neutron-rich super heavy nuclear regions. So this would avoid the second peak. So it should be known exactly from nuclear theory and experiment, hopefully in the near future. In our model, we parameterized the measured fission fragment distribution that's shown here. And fermium has single peak. It is almost symmetric fission. But this can be predicted theoretically by using the 4D multidimensional Langevin equation solutions to see the energy surface. If energy surface of assuming symmetric Barre is lower than asymmetric Barre, the fission fragment should be symmetric. So actually, as predicted, the measured cross-section, measured fragment distribution is symmetric. So we have extended this kind of formula towards very neutron nuclei, and this is a final calculated result of neutron star merger process. If we take the nuclear mass model and the fission models, including asymmetric, symmetric, or many fragment distributions, as suggested by a mass formula by itself, this is a result of fission recycling. But if we artificially...
Yes. 2-minute warning, sorry.
Okay. I will speed up. If artificially symmetric fission fragment distribution assumed, it is described in second peak. So we'd like to know the fission fragment distribution in order to know exactly what is the result of our process from neutron star mergers. The finally is a collapsar process. Collapsar exhibit more importantly the fission effect. The upper one is without fission and lower one is a fission. And as you see, the fission plays a very important role at later times. You see here. Now, fission recycling can enhance our process element this much. And also, weak rate dependence, which we have just studied in a couple of months ago, the reaction rate or weak rate, which take account of nuclear properties and Fermi functions with no temperature dependence, shows blue ones. But the approximate weak rate, by using Alcones et al. Result of just adopting the temperature dependence, which is a Pauli-blocking, the result are at least a factor of 2 or 3 different with each other. Okay, all these are the difference. And also finally, sensitivity to the light nuclear reactions in the collapsar is also very big. 1 or 2 orders of magnitude are depending on the reaction rate uncertainty of this one or this one. Okay, now time is almost up. Let me just speed up. Theoretically, these objects are probably strongly magnetized. So we should take account of the strong magnetic field effect by including the Landau condensation and other effect. Weak rate also changes due to the magnetic field. So we take account of all these. The Landau condensation make a final effect on the abundance through the weak rate, like this. The light elements parts, as well as the heavy elements parts, depend on the treatment of magnetic field effect. Okay, now, let me summarize my talk. We have studied first the galactic chemical evolution, and first conclusion is the early galaxy, as shown here at the bottom, was dominated by supernovae and the collapsar process without doubt because of the delay of binary contributions. And neutron star merger has arrived later in cosmic evolution. But all these 3 collapsars, supernovae, and neutron star mergers are equally contribute to the solar system process. So the quest for nuclear physics is to elucidate the light nuclear reactions, fissions, and weak rate or neutron capture rate and effect of magnetic field in each of these possible astrophysical sites of our process. So we can elucidate the important points. In order to find the final answer, it may take more time, but astronomical observations and theoretical calculations are really needed to crossing over together. Thank you very much.
Okay, thank you. All right, that was a great talk. Thank you very much. Does anybody have any questions? We have a couple minutes. Okay, well, I'll go ahead and ask a question then. So you mentioned looking at the effects of magnetic fields in these
Yes.
in these environments where you expect strong magnetization. In your simulations, what aspects of the magnetic fields do you vary, or would you consider varying first, like the strength or the configuration itself?
I see. Here, our study is on the collapses. So concretion is just a dipole magnetic field. We have collaborators of collapsal simulation guys, and 2D hydrodynamics has been done. And inside of a neutron star or near the black hole, not only the dipole magnetic field, but also rotational part are important, but extended strength is very, very strong. So we just simply assumed the poloidal magnetic field.
Okay. Oh, I see Alessandro has a hand raised.
Yes, that's me. Sorry, I'm listening from a cellular phone because I'm out of work, and so I hope that you will listen my voice correctly. I have just a curiosity. When you compute all these models, do you have a post-processing, or do you have a network that is coupled to the evolution of the merging of the binaries, or some kind of explosion you mimics in some way? In other words, the temporal evolution of temperature and density, how is this obtained? It is a one-zone model or some kind of a multi-zone model?
It is a multi-zone model calculated by Kolovikin, for example, in neutron star mergers. But I understand your point, that we have just adopted a dynamical ejector part. But wind ejector or some of a viscous ejector are needed to make a lighter part of our process. Depending on what you say, the neutron heated temperature increase or viscous, temperature heating as well. But these are known to be responsible for the lighter part of our process, whose masses are less than 100. So we just simply adopted a dynamical ejector arising from a simulation of ejector, 3D or 2D.
Okay, thank you.
Welcome.
Sorry, I see Yora, you have your hand raised.
Yeah, oh, okay. So Taka, very nice talk.
Yes.
Very nice talk.
Thank you.
Maybe it's a very naive question, but since you were discussing also the nucleosynthesis of light elements, do you think there might be any connection with the abundance of lithium? I mean, could this nucleosynthesis somehow affect the abundance of what we say primordial lithium in the interstellar medium?
Yeah, it is a profound question. Yes or no? If the very heavy, massive stars contribute, this could be a source of destroying lithium-7, because once primordial lithium-7 is falling into the massive star, first generation stars, for example, the lithium is destroyed very much, and ejector could be depleted. So primordial abundance may be altered. In this way, the very massive star, especially the first stars, may be related to the primordial lithium plateau and also the presently observed plateau. So I don't know at the moment, but once we make a model to explain the heavy nuclei, the hydrodynamics can be applied to the destruction easily to lithium beryllium boron. So we should do it. Thank you. But also, second point is some interesting scenario of our process is primordial black hole. And we are now studying that. Primordial black hole could be a very, very interesting and small guys, but at very high temperatures. And if this object can see the today's observed, very heavy black hole of mass between the mass gap between 60 to 120 solar mass, the primordial black hole is not ignored. So my idea is all these could destroy lithium-7, barium-7, or boron, or inversely could be a source of cosmic rays. So this is a very, very interesting subject, but we should think all these reactions together. First, theoretically, second, astronomically, and third, experimentally together. I'm sorry, I don't have any specific answer.
Okay, and then one last person, because we are kind of pushing the time. Catalin has their hand raised. You're muted.
Thank you, Taka, for the nice presentation. One moment in your presentation, you mentioned the contribution from the fission fragments from super heavy elements. And I wonder if we can reverse this question. Are there signs that super heavies are expected to exist from astrophysical observations, according to, of course, via the scenarios that you use for obtaining the abundances?
Mm-hmm. Okay, my answer is clearly, probably no. Because what we need in the super heavy element region is very neutron rich. Therefore, it can first decay through a beta decay, and then in a fission can occur. However, all these are not coming to the alpha decay regions as an extension of this, thorium, and also the island of stability around here. So there is a barrier of alpha fission, and also. Therefore, I don't expect in nature or in the universe, super heavy nuclei are, floating very much. And some could be created, but not very much.
Okay, thank you. Thank you.
Okay, thank you so much for your talk and for all the questions. So we'll move on to our next speaker, who is Grant Matthews, a professor at Notre Dame University, where he also serves as the director for the Center of Astrophysics. His research includes nucleosynthesis in stars, supernovae, and the Big Bang, as well as simulations of core collapse, supernovae, neutron star mergers, galaxy evolution, and Big Bang cosmology. So today he's going to tell us about nuclear physics issues in our process nucleosynthesis, and I will also give you the 2-minute reminder. And the floor is yours.
Okay, thank you for that introduction, and thank you to the organizers for a chance to speak on this topic. When I first was asked to speak, I thought, oh no, not another R process talk. I mean, it's something we've been working on for many years, and the progress has been slow. But one of the things I want to highlight is how the tides and eddies, the flows of our advancement of this field has developed over the years. So what I like about this is it gives me a chance to give a historical perspective on what we've slowly put together over the years. But first of all, I want to just answer the main question: what are the key reactions for the R process? It was nice Taka showed some light element reactions that are important, but what we've been saying since the 1980s and before was that it's heavy ion collisions. This happens to be a figure I just took off the FRIB website, but it kind of shows an artist's depiction of all the complications that come out of a heavy ion collision. And one of the things we want to do is be able to probe aspects of the R process. Now, the nice thing of a review kind of talk like this is it gives me a chance to shamelessly refer to my own works. It turns out that I've been involved in at least 4 review papers on the R process. The most recent one was in 2019 with Taka and Roland Deal and Baha Balentikin and Wako Aoki. And in the process of these different reviews, it's been interesting to see how the framework and understanding the R process has developed. Back in the earliest days, everyone thought they'd solve the R process. It was explosive helium burning and prompt ejection from supernovae. And then later on, we thought is probably low mass supernovae still in the 1990s. And then we got into the neutron driven wind, our process, and et cetera later on. And now it's gone over to binary neutron stars. And as Taka pointed out, the collapsar contribution is beginning to be understood. So it's been an interesting evolution, but just by way of overview, how does the R process work? It's just simple N gamma equilibrium. Sorry to go through such a simple matter, but it points out what we really need to know. In the N gamma equilibrium, there's just a nuclear statistical equilibrium. And all you need is a kind of nuclear Saha equation at a given neutron density. And that brings one to a path far from stability. And then as one arrives at this path, this is an old figure, I think it's even from B squared FH. As one arrives at this path, then there's a beta flow equilibrium, takes one up it. So what do we need? You need masses in order to get the neutron separation energies. You need spins and parities to get the partition functions. And you need the beta decay rates to calculate the flow along the R process path. It's that simple. Why don't we understand the R process yet? One of the key problems, as Taka pointed out, is the termination of the R process, which is shown on this figure. Even way back in B squared FH, it was appreciated how important the role of fission recycling is in determining the R process abundance yields. Let's see. Now, it was interesting. This came up in the questions of the last talk. My first paper on the R process was 45 years ago. It's hard to believe already. And in fact, a very popular topic at that time was whether or not our process could produce super heavy nuclei. And this actually illustrates the problem that's been with us for 45 years. Exactly where in those days we thought it was just neutron-induced fission. As Taka pointed out, beta-induced fission may be just as important or more important. But depending upon where the R process terminates, meaning when the fission barriers get low enough, one has a chance to produce heavy nuclei, at least back then. But in the more modern fission barriers, it looks like you won't get there. But it's actually a very important question. Taka showed this figure. Depending upon where you terminate the R process as you move up this path, if it's at a very heavy nuclei, you can get a symmetric distribution shown like this in the mass distribution. If it's lighter, you could get an asymmetric distribution shown here. And those are the ones that can give you maybe a better representation of the R process. Or in between, you could even get a 3-hump fission fragment distribution. And that's a big uncertainty that needs to be sorted out. The only way we'll ever understand it is somehow be able to probe the heavy region around, mass 280. Okay, the last thing, of course, in the R process is that eventually you run out of neutrons. You have to beta decay back to stability. And during this time, all of the processes have to be followed in a detailed evolution. Neutron capture cross sections are important. Beta delayed neutron emission, beta delayed fission, everything has to be taken at once. And I believe Rebecca will tell us some details about how various aspects of individual nuclei are important. One thing I wanted to mention is some of the progress that has been made in understanding details of the R process. This is an old R process figure from our 1994 paper on the neutrino-driven wind, but a recurrent problem has been the R process calculations tend to underproduce regions above and below R process peaks. And in our review paper in 2017 and in the paper we wrote in 2012, The determination of new beta decay rates has actually helped clarify this. In the 90s, we speculated that it might be systematics of the beta decay rates that cause these dips in the R process. And as better beta decay rates have been measured, some of this discrepancy, this disparity has been reduced. It shows the importance of understanding the detailed properties. And this is just a figure from our review of, the possibilities of probing. In this case, by the way, the heavy ion reactions that give us the beta decays are uranium spallation that were done at Riken. But of course, FRIB and so forth will have a much better chance, particularly important to try to probe properties of nuclei and beta decay rates near the 195 peak. We'll probably hear from Rebecca also the importance of mass models and understanding. Again, you have to produce the nuclei, determine their masses, determine their beta decay rates. So Taka briefly mentioned the models for the supernova. The one that we used to like back in the 90s was the neutrino-driven wind, which has fallen out of favor. I'll have some more to say about that. Ejection of neutronized material in low mass supernovae or magnetohydrodynamic jets, which are a moderate entropy. And then, of course, binary neutron star mergers, which is kind of a bandwagon effect now, since we've seen one that actually has our process material. But as Taka pointed out, the failed supernova that forms a black hole in a high temperature, high density accretion disk produces this MHD heated jet and makes a site for our process nucleosynthesis. And as pointed out by Brian Metzger and others, the collapsar rate is much higher probably than the binary neutron star rate, and it is able to provide our process abundances very early in the evolution, and it's a rare event. So it actually could explain many of the things that are being attributed now to binary neutron stars. I want to comment on the status of neutrino-driven wind. The idea is there's this huge flux of neutrinos, and the neutrino is a latent material for proto-neutron star, which in the old days, there was an asymmetry when we did the calculations in the 90s that the anti-neutrino interactions with protons behind the shock made a very moderately neutron-rich environment, which could produce the R process. Now, I want to say I've been working recently, and others have done this too, but I wanted to just give a plug for my student, Luca Baccioli, who will actually be the chair of a session later today. We've been reworking the one-dimensional core collapse supernova models based on a method developed by Sean Count called the simulated turbulence and reduced dimensionality. Basically, it just means in the 3D models that explode, the neutrino heated convection seems to be the key component. And there's a way to modify mixing link theory, and we have made a general relativistic version of that. This, for example, just shows convective velocities in a 3D simulation. And then by choosing a kind of mixing length parameter, you can match the basic convection properties. What I wanted to say is we made a study of the late time trajectories. And unfortunately, what we find is that, and others have seen this too, the asymmetry in the anti-neutrino neutrinos is energies is no longer there in the modern transport schemes, and one tends to have a brief time with lower electron fraction, meaning higher neutron density, but the long time effects that we saw before they tend to head towards a positive proton-rich YE, or even symmetric. So the wind, the conclusion is difficult in the modern transport codes to make a good neutrino-driven wind. And Taka showed that probably the neutrino-driven wind only forms the lighter nuclei, if anything, although it's probably valuable for the P process and the new P process. Anyways, I did want to make a point that we're also studying, which is an important application of reactions in nuclear astrophysics, is constraining the equation of state. As you know, nuclei have a saturation density around 16 MeV, but if you go to symmetric nuclear matter, there's an offset of 32 MeV, and this is density dependent. This is a slide I took from a talk by Sandeep Reddy, but basically this symmetry energy has a quadratic, or actually higher order, and in detailed schemes. But this is something can be probed by heavy ion collisions. For example, this is that linear parameter combination, the isobaric analog state, and heavy ion collisions. One can get some constraints on this. The biggest uncertainty in my opinion, in both supernovae and supernovae leading to the R process, and as we'll see, neutron star mergers, is this density dependence of the symmetry energy. It's a figure from PhD thesis of one of my students a few years ago. One of the things we've been looking at that I wanted to just mention is looking at a variety of equations of state that give more or less the right maximum mass of the neutron star of different symmetry energy dependence. How does that affect the explodability now that we think we know how to calibrate the spherical explosion models? And there's a very simple correlation, which I discovered was actually pointed out by Hans Bethe way back in the 1980s. Although there are many factors involved, what we find the strongest predictor of which stars explode is that the equation of state with the highest interior entropy, that is the heating per unit temperature, and it comes from, you know, how soft the equation of state is, how efficient it is at the neutrino scattering in the core. A little bit of a surprising result. I wanted to finish up talking about the ultimate heavy ion collision, which we'll hear many references to today, which is the binary neutron star merger effects on the R process. We're also doing some calculations in this I'd like to just showcase in a minute, but as Taka pointed out, and as we'll hear in Carla Frohlich's talk, the multi-messenger epoch has brought us a lot of information about our process production in the binary neutron star merger, which has produced this bandwagon effect that many propose this is the only source of the R process. By the way, in my lifetime, almost every decade, someone has gotten a prize or claimed we've completely solved the R process, and it was almost always, well, it's always been shown that no, it's more complicated than that. Okay, that's just an aside. Okay, what I wanted to talk about, Tak already brought this up, so I'm just going to mention that the delay time for neutron mergers, and Taka showed the work, the metallicity dependence, and that if you try to fit the metallicity distribution, you actually need, we noticed this way back in the 1990s, you actually needed a separate component of very massive stars, which we now attribute to the collapsar contribution in this paper with Yuta Yamazaki. Anyway, I won't go through it because Taka already did. I just want to talk about, again, there's a key equation of state issue in this very massive neutron stars. You probe directly, just like in heavy ion collisions, aspects of nuclear equation of state. The LIGO analysis uses a post Newtonian analysis. there are corrections for what's called the polarizability, how easy it is to deform the neutron stars. And the famous plot that's gotten better over time shows that only the most compact equations of state seem to be consistent with the data. This is contradictory to supernovae uh, uh, because in supernovae, you want a soft equation. Oh, I'm sorry, it's contradictory to the maximum mass requirement, because in order to get two solar masses, you want a fairly stiff equation of state. But both for supernovae and for binary neutron stars, you want a relatively soft equation to state in the compact star. But what I wanted to point out is that the post-Newtonian analysis is not the final issue. Neutron stars are not really quadrupole. Gravity's not post-Newtonian. There's very complex geometry that can come in. This is part of the motivation for a paper that my student Atul Kadia and Insang Su and Hee Kim and myself have been working on, was using fully relativistic simulations of neutron star mergers based on the Einstein toolkit, the exact solution, the field equations in a method called the BSSN. But more importantly, we've adapted it to investigate a variety of equations of state. And what we've discovered is there's something very interesting. One of the unique aspects of binary neutron star mergers is that as they go down to the black hole, it's unavoidable that they will pass through the transition to a quark gluon plasma. And the question is there an observable effect from the formation of this phase of matter that we barely can form in heavy ion collisions, but here's a unique laboratory to explore it. What we are seeing, although it's preliminary results, but I want to show them because I want to reference our own work. This is an example of two crossover quark hadron transitions. It's the QHC19 equation of state from Boehm and others. Not going into detail, but there's the difference between the two equations of state is the strength in the non-perturbative regime of QCD, the strength of the vector coupling and the di-quark channel. In C, the equation of state is much stiffer on this side. In B, it's a more moderate transition. Both transitions occur at the same time as, and both stars are the exact same simulation. Let's see, I'd like to show it again just to make a point. They're both merging at roughly the same, at nearly identically the same time. They both are on their way down to the black hole, but the quark hadron phase that has the higher pressure actually endures for a much longer time and has a much more striking ring down signal. That's what we show here. The green is the case of the 19C, where you have this extended ring down due to the fact that in the non-perturbative QCD regime, there's a higher pressure if the strength of the vector coupling is stronger. And both of these are approaching the merger at the same time. They both merge and go down to the black hole about the same time, but there's a very extended signal in the merger. So I just want to say, possibly in the future, as we observe more neutron star mergers, we may actually get this very interesting insight into a very important nuclear physics issue, which is what is the property of the quark gluon plasma. So with that, I'll finish up and just emphasize what I tried to make as the main points here. The key nuclear physics issues are: one, we need to know individual properties of nuclei far from stability, their beta decay rates, their neutron separation energies, their low-lying excited states. But probably the most important now to understand, particularly the role of collapsar and also the binary neutron star our process is the role of fission barriers and mass distributions and determination and the recycling of the R process, as Taka so well also pointed out. And finally, whatever constraints we can get on the equation of state of neutron-rich matter from laboratory heavy ion collisions or observing binary neutron stars will be a very important enrichment of our understanding of the nuclear physics issues relevant to our process, nucleosynthesis. And with that, I will stop. Thank you.
Okay, thank you for that great talk. We have lots of time for questions. I see that Carla has her hand up.
Nice talk, Grant. I wanted to ask whether you could go back to the slide where you showed the exploitability and the equations of state and comment a bit further what you found there, what you did and what you found there. I think that is a very important point.
Yes, let's just jump back here. This is, I believe this is the slide. Okay, here's the list of equations of state.
We can't see your slides, sorry.
Oh, that's right, I just stopped sharing. Okay, let me pull them up, hold on a second. Okay, let me just bring up the whole slide. Okay, yeah, I kind of glossed over this quick. This is showing the shock radius versus time for different progenitors, 9, 15, 20, 25. These are the different equations of state. And just some of these are density functional, some of these are relativistic mean field. There's another paper out by Schneider and others. They also looked at equations of state and decided that it was the effective mass that was the most important parameter. When we look at the combination of both relativistic mean field and density functional equations of state and things that are that were easily available to us, we found the common thread when you have a different types of equations of state is not the effective mass, but really the core entropy. Let's see. So consistently, by the way, the highest core entropy is the good old Latimer-Swesty 220 equation state for its liquid drop formation. And I mean, it's a fine equation to state, but it actually induces the highest entropy. And the worst case actually turns out to be the mean field, the Shen equation of state, which you know, here's the energy, for example, the explosion, which also has the lowest central entropy. Does that answer your question?
So they're all, across the equations of state, you'd used the same settings.
Yes, yes, it's the exact same star. We just changed progenitor.
But you kept the mixing length of the stir model the same.
Yeah. I didn't have a chance to go through the whole paper. I had another slide that I got rid of just before this.
No, I'm asking very technical questions here because it's interesting, but maybe I shouldn't block the discussion. Thank you.
Yeah, okay. Yeah, thanks for the question.
Okay, I don't see any other hands raised, so I'll go ahead and ask a question. And perhaps this is a bit, I don't know, naive, but did you see kind of like when you changed the equation of state, to what effect, and did it kind of affect the final abundance pattern that you saw with your collapsar models?
Yeah, we actually haven't run the R process yet. So I can't say what the final abundance was. Oh, wait a minute. You're talking about the collapsar model. The collapsar model we have not done with different equations of state. We have the model that Taka Kajina was referring to. We did old calculations with Ko Nakamura of our processing in the jet and then updated them, including the fission recycling. But in this case, the equation of state is kind of irrelevant because the whole thing's going down into a black hole. You're getting a high density accretion disk, which you have to kind of contrive to make it right anyway. And it's just material flowing out of that accretion disk that gets launched in the jet. So we did not do an equation of state study on collapsars, only on the neutrino-driven wind and the binary neutron stars.
Okay, thanks.
Thanks for the questions. Yeah.
Okay, well, if there are no other questions, then I will again thank the speakers and the organizers, and I will cede the floor back to whoever's turn it is next. Thank you.
All right, I suppose I'll take it from here. So thank you, Kelsey, for the wonderful job moderating the last session. And thank you really a lot to the speakers for the amazing and really informative talks. And I suppose now it's time to start the next session on astrophysical sources. I am Bharat Mishra. I am a first-year PhD student here at University of Catania and INFN LNS, and I work with the Pandora project, where we are trying to understand the effect of the stellar atmosphere on the beta decay rates. But I won't be fixating on my work over here. It's my absolute pleasure to start this session on astrophysical sources. And I'm very pleased to introduce our very first speaker of the session, Carla Froelich, a professor at North Carolina State University and university faculty scholar. She's a distinguished professor in the field of time domain astrophysics, and her work focuses on the prediction of multi-messenger signals from explosive events like core collapse supernovae. And this is exactly what she will be talking about to us today, as well as the effect of nuclear processes on these signals. So with this, I pass on the floor to her, and I really hope we have a really enjoyable session, learning a lot. As a note to the speakers, as always, I will notify you 2 minutes before your time is over so that we can wrap it up on time. And if there are any questions whatsoever, please feel free to put it in the chat or raise your hands. And if I'm a really terrible moderator, I will obviously see the messages in the chats more than I see the hands. So there you go, ma'am, and just best of luck.
All right. Thank you for the kind introduction. Thank you to the organizers for giving me this opportunity to speak here. And I would also like to applaud the organizers for selecting young scientists as moderators. I thought that was a very nice idea to do, and they've all done an excellent job. So I want to applaud the organizers for that. All right, now switching to the science, I'm going to be talking about, I had grand plans originally to talk about different types of supernovae, but to stay on time, even though the title says from explosive events, I'm going to focus on core collapse supernovae and their multi-messenger signals. Let's see, here we go. Of course, all of this work involves many people. I'm highlighting a few students and postdocs from my group, but of course, many more and many collaborators were involved. People to pay attention to are probably Noah Wolf. He's currently an undergraduate. He's graduating in a year's time and applying to graduate school, and I cannot highly recommend him highly enough. But all of these people that have contributed or listed here have done very good work, and you'll see some of their results in my slides. All right, so what I want to do is talk about core collapse supernovae, for which you see this little cartoon in the center, and talk about the different signals we can obtain from them, but also not only focus our telescope upwards, but also with a connection to basically focus the telescope downwards to the nuclear processes and how these things are connected. So here, this is a bit of a teaser, the type of signals you get from these different telescopes. So we have neutrino signals from 1987A. We have a current spectrum from supernova 1987A, light curves. On the gravitational wave front for core collapse supernovae, we only have predictions yet. We have not observed a signal yet. In the X-ray, we can observe composition as shown here from NuSTAR in the center, but also get indication again from the X-ray bands and possibly the compact remnant. I will come back to that a couple slides in my talk. In millimeter wavelength, again, we can get information about the dust distribution, but also hints about the compact object. And all of the things I'm going to be talking about, these types of signal, are always going to be in the connection of the nuclear physics and the nuclear reactions and nuclear processes depicted by this chart of isotopes in the corner, and make that connection. The results I'm going to show are from a long list of papers, which you see listed on this slide, and are based on this effective core collapse supernova model, which is basically a parametrization of the neutrino-driven mechanism in spherical symmetry. So it has an artificial heating term, but the artificial heating term is not tuned to achieve a particular outcome. This heating term is, you use one model to calibrate it, and then the calibration sets the settings for all the other models. So within our framework, all but one model are predictions. Also, I want to stress very much that all the quantities we predict are not independent. So if we predict the nickel 56 yield, we cannot change that independently of the explosion energy or the remnant mass. All the quantities are connected in a self-consistent way within our framework. And for some of the results I present, it's relevant to emphasize that we do not excise the central compact object that's forming, but we're actually following the formation and evolution of that protoneutron star at the core. And what this effective model allows us is to do lots long and large simulations, meaning we can do over 1,000 simulations of 10 to 15 seconds of GR hydrodynamics with neutrinos, followed by another 200 to 300 days of radiation hydrodynamics for photon transport. And we can include almost the entire star in the first 10 to 15 seconds, and obviously the entire star for the long-term out to a couple hundred days simulations. And these are all things that at the current time cannot be done by multi-dimensional simulations yet. And so we can produce ensembles of predictions of different messengers, and we can make comparisons of ensembles rather than individual simulations with individual events. All right, so starting, core collapse supernovae are the explosive death of massive stars. So we need to start with the massive stars. We heard yesterday a very nice talk by Alessandro about massive star evolution and where the key nuclear reactions, how they affect the structure and the evolution of the star. And some of these effects, as Alessandro pointed out yesterday, that you will see an imprint of those also in the signals from the core collapse supernova. For example, the final core size of these models when they start collapsing will have an impact. What the instabilities doing and the different burning shells, how they set up the structure during the evolution, that impacts the signals from the core collapse supernova. And also the mass loss during the evolution will impact what the signals look like. So the figures I'm showing here in this slide are sets of progenitor models that we used in our studies, and they're for different mass ranges. So the horizontal axis that you can't read goes from 10 to 40 or 10 to 70 solar masses. The four different colors give you four very crude structure of the star. So the black at the bottom is your iron core, the blue depicts the carbon oxygen core, the narrow yellow band is the helium shell, and then the red on top is your hydrogen. And you can see that at the left, where you have solar metallicity progenitors, there is mass loss. The envelope of the red hydrogen is not a monotonic function of the initial mass. These stars, the heavy stars at solar metallicity, have lost their hydrogen envelope. They have even lost their helium envelope out here. Versus if you look on the right, if they're at low or zero metallicity, there's virtually no mass loss, and they retain their large hydrogen envelopes. And as you increase in core mass to the right, your final massive collapse also increases, and it's pretty much the same massive collapse as it started out with. These properties will become, you'll see when they become important again when I talk about the signals, especially the electromagnetic signals. So one of the first types of signals that we can predict are does the star explode or not? And so this is, you have your calibrated series, you take different progenitor models, you explode them, or you run them through collapse, you watch what happens, and you color code whether it explodes or not. And so these two plots on the left and the right, they show you 4 series of progenitor models at different metallicities. And basically the color says, if at any particular ZAMS mass there's color, it means that model exploded, and if it's black, it didn't explode. And the left and the right are 2 different, slightly different setups, and you can see that overall they look almost the same. If you look very carefully, you'll see a few minor differences. And this comes from exactly how you calibrate has a small impact. And as Grant said, the nuclear equation of state has an impact. But overall, we can conclude that at lower metallicities, we have lower explosion energies and generally form more black holes for the same distribution of initial masses. And based on those explosion or basically the outcome of our simulations, we can then proceed to calculate and predict more observables. So the first monthly messenger signal or observable are the remnants that are left behind. So if you have, in a very simple picture, if you have a successful explosion, you end up with a neutron star. If you have an unsuccessful explosion, in whatever way that ends up being unsuccessful, whether it starts to explode and fails or whether it's direct collapse, but the end point is a black hole. And so again, we have for solar metallicity on the left and right outside of the slide, and for low and zero metallicity at the center of the slide, we have on the left neutron star mass distributions, on the right black hole mass distributions. And while there's no unexpected large difference between, say, different neutron star distributions, there are some differences, again, depending on how they're calibrated and which equation of state you're using, which progenitor models, what you set up. But basically, we can predict distributions of remnant masses that can be compared to observed distributions of these remnant masses. This, in particular for the neutron star mass predictions, supernova 1987A is the best studied core collapse supernova, and there were 2, one from this year and one from 2 years ago, recent observations on this question of where is the neutron star of 1987A, or what compact object was left behind by 1987A. And so on the left, you see, so this is not our work. So on the left, you see observations from in the millimeter with ALMA, and you see in blue, the ring structure, and then at the center, there's this inset, which you see on the left, and there's this hot, bright blob here, and they call it the hot blob in this dusty core. So all this red center part is rich in dust of 87A. And the interpretation in this paper is, could this excess hot blob of dust be a signal of the missing neutron star of 87A that we've not detected yet? From just earlier this year, there's another paper on the right from X-ray observations with Chandra. And so you see again the ring, and at the very core, they detect non-thermal emission in the 10 to 20 keV range. And they discuss 2 interpretations, a diffuse shock acceleration or a signal of a pulsar wind nebula. And they compare with MHD simulations, and the conclusion is, while they cannot rule out diffuse shock acceleration, it is more likely that this non-thermal emission that they see is the effect of a pulsar wind nebula. So this is an ongoing, unfolding story, to use words of the popular media. Eventually, we will know whether this is a neutron star or a black hole and what the mass of that neutron star is. And then we can go back and compare it against simulations like these. For our 87A model, what did we predict for the neutron star? If we match everything else, like the light curve, then the yields, did we also match a neutron star mass? So this is a teaser. We don't know the answer yet, but this is ongoing. All right, other observable signals in this multi-messenger area are explosion properties, and of course, nuclei. And so on this slide, I show you two plots that have the same quantities. They have explosion energy on one axis and ejected nickel 56 on the other axis. In our models, these two quantities are not independent. And so where the colored dots fall, we have this is not a vertical or horizontal line where they can be moved around. They fall, and there's one explosion energy with one ejected nickel mass for a given calibration for a given progenitor. You can also see in black and gray observational data from supernovae. The black crosses are the same on the left and the right. The left plot has in gray additional data. But basically, as a bulk, these simulations, we can compare the messengers, the ejected nickel 56 and the explosion energy with the observed same quantities. You can see that overall, we reproduce the same trend, even though this needs further investigation, further discussion. These points that seem to be low explosion energy with relatively high nickel that are both in the observations and in some of our simulations. But by being able to do hundreds of simulations, we can compare bulk from the simulation with an ensemble of observations. All right. Moving from remnants and explosion properties more to the nucleosynthesis, the nuclei are an often forgotten but very important messenger. And the main contribution of core collapse supernovae that originates in the explosion rather than in the progenitor are iron group elements. And so here I show you 4 plots of iron group elements are labeled across the bottom. The amount is measured in this observer's X over Fe, where if you get, it's relative to iron, relative to solar. So if the point is at 0 on the vertical axis, that means the same ratio as in the sun. And these 4 plots show our simulations in color against a well-studied metal poor star depicted by the triangles. And I say well-studied because they derived abundances both from neutral species and from ionized species in that stellar atmosphere. And as you would hope, they give the same answer or almost the same answer. And then our simulations, again, we can do an ensemble of simulations and compare that against the abundances seen in metal poor stars. And you can see that some elements have a wide spread of outcomes depending on the progenitor used. Other elements have they always more or less give you the same amount. This is for a fixed calibration, a fixed equation of state, and a fixed set of reaction rates. If you vary the reaction rates of iron group elements within their uncertainties, these points will look different. And how they will look different, I will postpone that result to the in-person workshop, hopefully next year. All right, we can not only look at elemental abundances in metal poor stars, we can also compare against observations of long-lived radionuclides, for example, like titanium-44. And so this is just one example. On the left, this is work by Ivo Seidensal, where they fit the light curve of supernova 1987A with a 5-component fit for these long-lived radionuclides of titanium, cobalt, nickel, 2 cobalt and 2 nickel isotopes, and from that derived an ejecta mass of these isotopes. Now, for example, the titanium is notoriously problematic to synthesize in sufficient amounts in spherically symmetric simulations. There's 2 key reactions that contribute, the calcium-40 alpha gamma and the titanium-44 alpha P reaction. There's a measurement from 2014 of this titanium-44 alpha P reaction where they find a cross-section that's about a factor 2 smaller than what was commonly used before. And when we do that, a smaller cross-section of titanium-44 alpha P leads to higher yields of titanium-44. Now, those yields are still much lower than what we get inferred from observations, we've also looked at, so these are spherically symmetric models, so mixing is not something that naturally happens. And so if you put in a prescription for mixing, the mixing can increase the yield of titanium-44 that's ejected. And if you combine the two, the smaller cross-section and mixing, you can, each of them increases the yield by a factor of a few. And so then you get within the error bars of the observationally inferred titanium. So this is something that needs to be further investigated and that we are currently further investigating. All right, so we've had compact remnants and nuclei, explosion properties and nuclei as messengers. I want to shift gear now and move to electromagnetic messengers or observables. So what we've done with these models, so far I've talked, if you look at this flowchart on the left, we have progenitors, they're described here, and then we ran them through our effective 1D model, and we get explosion properties and nucleosynthesis yields. We took this 2 steps further, and we reappended the envelope, and we continued running these models through radiation hydrocode and then a Monte Carlo photon transport code to get both bolometric light curves, broadband light curves, and spectra. And these are, again, if you do this for many models, these are things that at the present time cannot be done in 3D. So we've done this, and I want to show you some of the key results we found from that study. So on the light curve side, it turns out that our light curves, when we just do this on all of our exploding models, fall into roughly 4 groups. And these 4 groups are defined by the quantities that are on the axis here. The pre-explosion radius on the horizontal axis and the hydrogen envelope mass on the vertical axis. The different points, the different colored points tell you the metallicity. So blue is solar, green is low metallicity, and orange are zero metallicity models. But they fall into these basically 4 quadrants indicated by the dashed and dotted lines. And when you look at which models fall into which quadrant, you'll see that they have progenitor properties in common. So for example, the top right corner, large pre-explosion radius and large hydrogen envelope mass are these less than 20 solar mass models of solar metallicity that have a large hydrogen envelope, and they're extended stars. On the extreme other end, small pre-explosion stars with few or no hydrogen left are your, again, solar metallicity models with mass loss, but the higher SAMS mass models that are stripped and lost their hydrogen. And then the other 2 quadrants are your solar metallicity models of sort of somewhat stripped, but not fully stripped models in the bottom right. And then all your small pre-explosion radius models, but large hydrogen envelopes are your low and zero metallicity models that retained their massive hydrogen envelopes, but overall are always more compact than the corresponding solar metallicity stars that have extended fluffed up envelopes at collapse. And so the light curves for these 4 groups are given again in the corresponding corners of this slide. So we have on the top right, what we consider normal type 2 supernovae. Plateau, so you see an extended plateau phase about 100 days, and then you see the radioactive tail for these models. In the top left, you can see the 87A-like models that don't have that plateau phase, and they actually rise to their peak luminosity sort of on the time scale between 50 and 100 days, and they're opaque and not very bright early on. Bottom left, you have your typical stripped envelope light curves that are kind of like the 87A, but they're much broader peak here in their peak luminosity. And then there's sort of these transition models that we show on the bottom right that are kind of in between the type 2Ps and the stripped envelopes. So we can predict, again, ensembles of light curves that can be compared against observed ensembles of light curves. And one thing we did, and in fact, undergraduate Noah Wolf did, is a statistical analysis using a technique called active subspace sampling to identify what is the most important parameter or quantity that sets the luminosity at 50 days and the time to peak, whether it's a fast rising or a slow rising light curve. And you can see from these plots, the quantities we looked at are on the bottom. So ZAM's mass, mass at collapse, radius at collapse, hydrogen envelope, explosion energy, and nickel 56 mass. And the vertical axis tells you basically the larger that active variable weight is, the more important it is. And not surprising from the physics, the amount of nickel 56 really determines how long it takes to rise to peak and what the peak, the luminosity of 50 days or at peak is. All right, we also predicted spectra. So we have an entire ensemble of spectra. On the left, I show you the example of the temporal evolution of the spectrum for, I think, an 18 solar mass model. And on the right, you can see that we, for example, can see the iron line blanketing in this grayish band here. The details of these spectra are not as important. The more important point is that we have, in this particular paper, we have 60-something light curves and 60-something spectral evolution available that we've calculated, and the data is freely available. You can get that either from the journal website or from our data website. And we do hope that more comparisons to observations than we have done and can do will be done, and that will help us doing these ensemble comparisons to further understand what do we get right in our current understanding of supernovae, and what do we not get right, and possibly even can we constrain some of the either reactions or nuclear physics, the equation of state, quantities like that, can we constrain them by having, instead of a few models available to compare, having entire ensembles available to compare to observations. All right, so here, while I stress the importance of comparing to ensembles, we actually have compared against an individual supernova. This is 1999 EM. It's a low mass progenitor, so order of 12-ish solar masses. And so we're comparing against a 12 solar mass model of us. And on this slide, which is pretty busy, we're showing a lot of different things. So let's focus on the right 4 plots first. These are broadband light curves. The open circles are the observed light curves in broadband, and then the lines are the predicted or calculated light curves in the same broadbands. And you can see that in this particular case, except for the shortest wavelength here in U and a little bit in B, we get, in the trend, we get a pretty good match. And this has not been tuned to this particular supernova. This is just one of the low mass models that matches in progenitor mass to 1999 EM, and plot that against the observed data. On the left, we show bolometric light curves from 2 different codes. So the top is from the SNEC code, which is just radiation transport and does bolometric light curves. The bottom light curve is a bolometric light curve from the Monte Carlo radiation transport code SuperNew. So the 2 codes for the same model predict slightly different bolometric light curves, as you can see in the shape of the lines versus the data points, which are the same in both plots. But these plots also show the importance of the one feature we really cannot capture in our setup, which is the mixing. And so what we've done is here, this is the only hand tuning piece of the pipeline, is rather than taking the standard number of 0.4 of a boxcar mixing length, for a couple models, we played around with that boxcar mixing length to quantify how different the results are. And so what you see in those 2 plots on the left is going to more extreme mixing, either box curve 3 or 2, which is pretty much a fully entirely homogeneously mixed ejecta. So that's kind of your upper limit of what's possible for mixing at all. How different those bolometric light curves look like from a standard setup, which is shown in dark blue in both of these plots. So we can quantify the one aspect we don't include in our models, which is the mixing, but we can also investigate the impact of different core structures, the impact of different reaction rates. With this pipeline, with this setup, we can very easily do not just a few models, but entire ensembles and test all of these different important pieces and figure out how they would, if at all, show up in the observables. All right. I may be a little bit ahead of time, so maybe I'll show one more slide after conclusions, but we'll see. So let me conclude this part first, which is we have an effective model, and I showed you some results of that, that basically allows to do thousands of simulations out to several hundred days and predict a slew of different messengers that can be compared to observations. And the observables that we have predicted so far, explosion properties, remnant properties, so that's neutron star and black hole masses, detailed nucleosynthesis yields, light curves, both broadband and bolometric, and spectra out to the nebular phase. And really the key thing here is that that allows to do comparisons of ensembles of simulations to ensembles of observations. I believe I have about a minute or two more, is that right?
Yep, absolutely. Yeah, you can go ahead.
All right, so I'm going to, without going into the details, I'm going to show you one slide of a different type of supernovae where the same idea of multi-messenger applies. And so pair instability supernovae are your very massive stars, so 100 solar masses and above, that in their evolution, they only reach an oxygen core. And once they have an oxygen core, because they're so massive, the temperature is high enough that you start doing pair projection. So you're turning photons into electron-positron pairs, which reduces the photon pressure, which leads to a collapse of that core. And you ignite the thermonuclear explosion, which completely disrupts those massive stars, or very massive stars. And so one of the key differences to the core collapse supernovae is that we don't expect the compact remnant from them. And their ejecta masses are much, much higher because their initial mass is much, much higher. And so we've done similar multi-messenger work for these pair instability supernovae. And it all started with my first graduate student, Matthew Gilmer, doing the first 3D simulations of these collapses. And the image I'm showing you here is showing you that if you do this in 3D, while overall the structure remains spherically symmetric or close to spherically symmetric, you see that mixing becomes important at composition interfaces. So this shows the silicon to oxygen interface where you see this mixing. So the color coding is silicon, with red being the high silicon. So this is your silicon layer extending, mixing into the oxygen that's further out. And then based on these simulations, we, excuse me, we predicted light curves for these models. And what you can see is, unlike the core collapse supernova light curves, for these models, the more massive they are, so in light blue and red, they give very, very broad and very, very bright light curves. So their time to peak is much longer than for core collapse supernovae, and they're much brighter. The blue line here, the P150, is a pair instability supernova light curve, but this looks much more similar to a core collapse light curve. We've also then calculated spectra, and this plot that is very busy has comparison of 1D to 2D to 3D, and whether you take angle average data or the full 3D composition. But basically, we can do, and we have done these predictions of what the electromagnetic signal would look like. So if you ever observe something weird, you can go look at all the theoretical predictions and see whether there's something that could match the weird object you observed. We've done neutrino signal predictions for these parent-stability supernovae, and they're from thermal emission of neutrinos from the large amount of iron group elements you're making in these thermonuclear explosions. We ran them through an entire pipeline to get basically the expected detector rate on Earth for these different neutrino detectors, Hyper K, Super K, June, and Juno. And the signal will be different whether you have normal hierarchy on the left or inverted hierarchy on the right. And then continuing the investigation of mixing, we've extended this to investigating the nucleosynthesis. So also for these, to wrap up this slide, for these types of explosive events, the parent-stability supernovae, we can predict electromagnetic signals, the nuclei, and in this case, the neutrinos, and there is no compact remnant, so there's no remnant mass distributions to predict from these. So with that, I see my chair's video come on, so I take that's the end of my time, and I'll thank you for your attention, and I go back to the conclusions, and looking forward to your questions.
Well, thank you very much, Professor, for that really well-rounded and informative talk on how exactly we can study parent-stability supernovae and crook-collapse supernovae using different kinds of signals. We already have a slew of questions over here, so I suppose I'll give the floor to Moshe Guy for the first question. So please go ahead.
Yeah, concerning 1987A, first, forgive me if I'm asking something you addressed. I had some temporary issue with my internet. So we know pretty well the progenitor star for 1987A. I recall it was a blue giant, 17 solar masses. Well, that's precisely where nuclear physics starts to get very interesting, whether it collapsed to a neutron star or a black hole. Could we, for example, two effects, one would be the equation of states, the other one would be the cross-section of C12 alpha gamma. Let's assume for a moment that it ended up as a neutron star. Can we put any constraint on both the equation of state and C12 alpha gamma from the fact that we have observed, let's say we would have observed neutron star?
So we can, the alpha gamma rate is of course whatever the stellar evolution modeler whose model I'm using has used. So that's, when it comes to me, that's fixed. But of course you can imagine a situation where you run multiple stellar models with different carbon 12 alpha gamma rates and then collapse them the same way. Yes, we can, in our setup, we can get out. So for a given progenitor and a given calibration of the method, we can predict or get out whether it explodes or not. And that also, if it does explode, we'll get out a neutron star mass. And if it does not explode, we can eventually estimate the black hole mass of the object. And so you can imagine, and I think that's not a far stretch from the results that Grant showed, that different equations of state will give you either an explosion or a non-explosion for the same progenitor, with the same carbon 12 alpha gamma rate. So I don't think we can narrow it down to one, but I think we can narrow it down to say a group of equations of state that will be compatible with all the other observables of 87A and the neutron star, and then have a mass prediction so that when it gets observed, one can compare whether the prediction matches the observation or not.
Yeah, isn't it true that the equation of state has to be pretty soft in order for 1987A to end up as a black hole? I see Taka is really chafing at the bit to get involved in this discussion.
So we've looked at blue supergiants and red supergiants, and it is pretty hard to get them to turn into black holes for those lower sort of, as you said, 17, 18 solar mass progenitors. But with a sufficiently pessimistic calibration, one can get some stars in the right mass range to do black holes.
Thank you.
All right, so thank you for the answer and for the wonderful question. So since I'm going in order, I'll give the next option to Grant Matthews. So please go ahead.
Oh, just a very quick question. Since you brought up the pair instability supernova, as you know, LIGO has evidence that some black holes appear to avoid the black hole mass gap. I wonder if you had any insight on that from your simulations.
Can you repeat that? I had a bit of
the
children noise in the background that overpowered you.
The pair instability supernova produces what's called the black hole mass gap. No black holes between 40 and 120 solar masses, but LIGO has some evidence that their largest merger actually has a black hole inside the mass gap. I just wondered if you'd spend any time trying to see if you can circumvent the black hole mass gap in your studies yet.
I would like to do that. I've not had the time or the person power so far. It's also, I should emphasize, and I'm sure you're aware of that, that the pair instability, both the stellar evolution models and the basically, what is their final fate? Will they pulsate or directly explode? Is very uncertain. So I'm sure there's a lot of room to investigate and quantify what combinations would maybe avoid the mass gap. But I don't have an answer, but it's certainly a question that somebody should look into. Thank you.
Thank you. All right, the next question will be from Alessandro Cieffi. Please go ahead.
Hi, Carla. Very nice talk. I have essentially three comments. The first one is that the one-to-one relation between nickel and kinetic energy of the ejecta, but this is valid for any relation, holds only if you do not include rotation. If you have a spread of rotational velocities, you may expect for the same kind of or mass or whatever to have different outcomes. So you don't really expect a one-to-one relation. We know that stars rotate, do not rotate with the same velocity. So this is actually what we do.
Yeah, that's absolutely true. The model results I showed were for non-rotating models. What I meant with my comment is something that often referees ask about is, can't you change the nickel mass and keep the same explosion energy and then get a better match? And we can't do that in the setup. They're not independent, but you're absolutely right. The relation, the line where they fall depends on whether you have rotation or not in the initial model.
Yeah, the second comment is about titanium-44. In addition to the reactions you mentioned as important, there are two other things that must be considered. The first one is the decay time. How I told yesterday, at high temperature, the decay time of titanium-44, like all the others, falls enormously. So we must be sure if the decay time is that one. And in our paper in 2017 on titanium-44, we showed that with rotation, the amount of titanium-44 made hydrostatically in oxygen burning that usually is neglected because it occurs usually in a radiative environment and then is destroyed by the shock wave. If you have a convective region, you can preserve titanium-44. You can produce a quite large amount of titanium-44 because you preserve the hydrostatic one. You put in another layer. So the decay as a function of temperature is another critical point. And the last comment concerns something that yesterday I said is trivial, but we must always remember this. Carbon-12 alpha gamma. Carbon-12 alpha gamma is needed to understand how much carbon we have at the end of helium burning, but it's not enough. We need that carbon because we want to know how far the carbon convective shell advances in mass. This is what we want to get. This depends on the carbon abundance, but also on the efficiency of the carbon-12, and on the efficiency of the mixing that we assume to be like we have in the sun, but we are certainly wrong, but this is what we can do at the moment. So all the discussion about the final phase of the star should be put in terms of efficiency and advancing of the carbon burning shell. That depends, among the others, also on the carbon-12 alpha gamma.
Yeah, so basically, I think I can thank you for your comments. I agree with all of them. And I think it shows that even though I showed a multidimensional picture of these messengers, it's only still a slice through one dimension. And there's these other additional dimensions that also need to, like having different rotations, having different efficiencies of carbon-12 alpha gamma. And that turns the whole problem in a multidimensional space that needs to be investigated.
But that's funny.
Yeah, no, it keeps us in business, right?
Thank you.
Yeah. I think Taka is burning to ask a question.
May I?
Yeah, please go ahead. Please go ahead.
Okay, yes. Carla, I have a question, very simple question about the pair instability supernova and the mixing efficiency. We are interested in hydrodynamic effect in pair instability supernova. And my question is, if for some reasons carbon abundance or oxygen abundance or magnesium abundance changes by factor of 2 in the surface, the spectrum change? If yes, how does it change?
So the spectral investigation was really only focused on, the multidimensional hydrodynamics effect. So basically how strong this mixing was and how much of an deviation from spherical symmetry you get. So I cannot quantitatively answer the question if you change the surface abundance by a factor of 2, how much that would show up in the spectrum. But what I can tell you is that deep inside, even small deviations from spherical symmetry, so small changes in the abundance at any given radius, does show up in the spectrum. So my prediction would be that it will also show up for the surface abundances.
Good, thank you. I hope so.
I'm curious to see the results.
All right, enough. Thank you.
Thank you very much, Taka. Thank you very much, Professor Carla, for this really amazing talk and for answering all the questions so beautifully. And it was a really lively session, I must say. So for the moment, since we're running a little bit behind schedule and it's, as I say, the best time of the day, it's coffee time. So I'll stop the recording for some time. We will reconvene at 4:35 exactly with the next speaker. So till then, everybody have a good coffee and we will reconvene in a couple of minutes.